Recognize the image here? Some of you might recognize the image here from the respect of this being St Bees. This is looking from St Bees on the Cumbrian coastline, northwards up towards Whitehaven and Fledswick Bay, if anyone's ever been around there. Classic area for some of the Triassic age red beds that we see. We call red sandstones typically red beds, just as a colloquial term, because they're red in color and they tend to be bedded sands. But let's the Cumbrian sandstones themselves, the red sandstones, are particularly important in Cumbria and various portions of Dumfries and Galloway, along the western portion of Hadrian's Wall itself. And I suppose most people are familiar with going into Penrith, perhaps, or if you go across into Cumbria and go to St Bees, you'll see buildings built of red sandstone. And as you're driving through, you probably will think, oh, that sandstone, red again, another red sandstone, they're all the same. Well, they're not. There's a lot of variety amongst the red sandstones that we see in Cumbria. Firstly, they are probably around about 100 million years of difference in ages between each of the sandstones, and there are differences in the way they were actually deposited, how they were formed back at the time. I'll come back into how they were formed a bit later on, but purposely most of them were used for building stones. We can see lovely houses, and even modern day builders are still building them, usually framing windows with the Penrith or St Bees sandstone. Of course, the associated with this red coloration is iron ore, and iron ore has been used for steel making, mined in Cumbria for many hundreds of years. It stopped back in, I think, 2007 was the last mine, Florence mine, which mined out an iron ore. Not directly related to the red sandstones in that they occur together, but of course the occurrence of the iron ore is what gives the red sandstone its color, and I'll come to that in a few minutes. Associated with the red sandstones, of course, is mining of gypsum because of the environment of deposition of these ancient sandstones. If anyone's gone across the A66, and near to Penrith, you have a village called Kirby Thor. It's just, you turn off from, I can't think of the name of the village on the 66, but it's where there's the speed cameras are there. It goes down to the single carriageway. And you'll see in the distance plumes of steam or water vapor coming out, and you always wonder what's going on there. Whereas the Kirby Thor mine, where they're taking out gypsum and they're dehydrating it slightly because it's calcium sulfate and 2H2O. They dehydrate it, it makes it slightly more robust, and they use it for gypsum plasterboard, plaster products. Very important indeed. And it comes from the same age as the sandstones you see around Penrith. But so it's a local environment that was deposited at that time. Oops. But of course, I suppose for you guys, there's also a local importance, not only from perhaps in Hadrian's Wall, but along Meg. There's the Bronze Age stone circles, or stone circle with, from what I've seen reported, of 60 plus stones of all different origins. When I've been there some years ago, I thought some looked like glacial erratics myself and weren't actually necessarily placed, or maybe only locally moved. But the Long Meg stone itself, which is about 12 feet tall, is made of Penrith sandstone, which is locally sourced. It has to be locally sourced. In fact, you can walk from the location of Long Meg to a few exposures where it probably might have actually come from. It's got all sorts of carvings on it, but the classic giveaway that this is Penrith sandstone is you can see at the bottom of the actual Long Meg itself, it's very bright red, brick red colour, which is very characteristic for the Penrith sandstone. That brick red colour really is important. And what makes a red sandstone red? Well, you can see here, this is a close-up view of the Penrith sandstone, and although it looks a bit granular probably on your screens, It's certainly made up of lots of grains of quartz, a very robust mineral, resistant to weathering, and that's why lots of sands are made of quartz. But the little white blebs in it are what we call feldspar. And so there's a few odd feldspar crystals in here. Some of the white, they were also kind of etched quartz, kind of have a frosted form to them as well. But you can see the red coloration is evenly spread throughout the rock. There's little bits of white, but that's actually because of a reason. Now, I was going to show you all a 3D rock viewer. I'm more than happy to share this with you all afterwards. I've tried using it several times this morning and it seems to just keep on crashing on me. And what we have is we scan our rocks in Durham purposely for the students. And so you can rotate the specimens around in 3 dimensions and you can zoom right into the sample and zoom right out. The software, the 3D rock viewer software, is freely available online. And afterwards, I'll pass on to Ian details, and I'm more than willing to share the files with you. They're only about 30-40 megabytes, the file size is, but for some unknown reason, the 3D rock viewer isn't working this morning online. So it's a shame, but we'll just show you a close-up of that previous image I've shown. So why are they red? Why are sandstones red? Well, the thing is, no sands are deposited red to begin with. So that's something to bear in mind. They become red over time, and usually over geological time. And they become red because of hematite. Sometimes spelt H-E-A-E and sometimes spelt H-E-M. Doesn't matter. I prefer H-A-E. I think the other ways are a bit of an Americanism. But typically, and there's a lot of text on here, but I just want to show you a few key points, is that hematite is a naturally occurring mineral and it forms in various different ways, but typically you can see that the 2 bottom images here show hematite in its kind of metallic grey colour and also in its reddy brown. The reddy brown to red colour is what gives sandstones their red colour. You only need about 0.1% of hematite to be within a sandstone to make it red in colour. However, when they're initially deposited, sandstones tend to be a buff grey colour. You don't go to the beach anywhere in Northumberland or along the Durham coast or even along the west coast of Cumbria and find red sands on the beach. It's not a common occurrence. You can in some parts of the world, but certainly not in the UK and most other places. And that's because there could well be iron within the system, but it hasn't changed to the form that we need it to change to coat the grains. And the hematite, iron is present in most sediments, but particularly in sandstones. So over a period of time, small quantities of the iron mineral start to break down and they become oxidized. And for those who are into chemistry, we take it from an Fe2+ state, which typically is green color, to an Fe3+ state, which is the oxidized iron. And this kind of like thinly paints the individual grains of quartz within the rock itself. It produces a thin veneer over the surface. That in its own right is great. That doesn't necessarily give it its color, because you can sometimes have hematite, which is actually this silvery gray color. But because hematite crystals absorb all the light except for red in the spectrum, and they reflect that out, that's why you get sandstones which are red. So essentially, it's to do with the burial process that become red sandstones. So we only see older sands, not modern day sands, which are red in color. And that's why when we look at sandstones in the rock record, we can oftentimes, we go back to Permo-Triassic, which is what we're looking at here today, or we can go back even older to perhaps Devonian times and Devonian sands, which are called the old red sandstones, because they're red in color as well. And their red coloration is purely down to hematite as well. Hematite as a mineral is Fe2O3. It's a very stable form of iron oxide. It precipitates over a wide range of conditions, pH conditions, so poor fluid conditions essentially, oftentimes associated with hydrothermal mineralization, later stage. And of course, it's a really important iron ore mineral. which in the UK is perhaps less important now than what it has been in the past, but many parts of the world, hematite is incredibly important. It comes sometimes from tropical soils, where in places like Jamaica, one of Jamaica's largest exports currently is iron ore from the soils there, or it could actually also come from directly stratigraphy. So lots of Australian exports of iron ore come from Pre-Cambrian age rocks called the banded iron formations, and those are dominated by magnetite, hematite, and quartz. Very odd situation that occurred back in Pre-Cambrian times, which gave rise to that precipitation of the iron directly from seawater. Iron is biolimiting now, so iron is not found in seawater, so iron doesn't precipitate directly in that mechanism at all today. So something very weird happened back in Pre-Cambrian times over 590 million years ago. So red sandstones are red because of hematite and iron oxide on them. You need very little and it makes them red in color, but that only happens after they're being deposited through geological time. I'm talking here probably tens, if not hundreds of millions of years for that to take place. And Cumbria has been a really important place for mining of iron ore. And the Florence mine near Egmont, which is over near St Bees on the Cumbrian coastline. I don't know if anyone's ever been there. I think there's some sort of craft centre there now. I haven't been for a few years, but they mined out beautiful botryoidal hematite, absolutely spectacular, world-class samples, and you regularly see it selling for hundreds of pounds on the open market now even. And you can see it forms like this sort of globular form on the surface, and it's just the way it precipitates straight out of pore fluids, giving rise to this classic form. It doesn't precipitate like that in sandstones, it just forms a thin veneer, and we'll look at that a little bit later on. Of course, iron ore itself, or hematite, is particularly important, and NASA have been very interested in this for many years because it's what gives Mars its red coloration. You can see there a Mars Curiosity rover image from the Whale Rock on Mars, which shows some beautiful sandstones with what we call cross-bedding within it, showing that perhaps there was water at one time, allowing those cross-beds to actually form. And we're going to see a bit later on when we go to look at the Penrith and we look at the St Bees sandstone, cross-bedding that would look exactly the same as that. And we know what formed those processes back in the Triassic, so we can use the same hypothesis to assume that on Mars the same happened. What we do see on Mars, though, is something we haven't seen on the surface of Earth, and that you find these hematite blueberries. They do look like blueberries, but they're spherules of hematite. Look a little bit similar to the ones you can see in the kidney ore in some respects. And because this is giving some hypothesis that there could be water, or was water at one time on the surface of Mars. If it wasn't the cross-bedding that gave it away, I think the hematite and the precipitation of those, which requires some water, certainly helps to support that. So a lot of research is going on at the moment about trying to understand, is Mars possibly a habitable planet? NASA's investing tens of billions of dollars into it. And believe it or not, most of the input into understanding the geology, what makes up the rocks, the geochemistry on the surface of Mars, they're having to come back to the UK, and various UK geology departments around the country are helping them with that, because the American system is very different to the way we teach here in the UK. We still, you could view as a little bit old-fashioned, we still actually teach the basic petrography of looking at the rocks, identifying processes from them, and then making interpretations. The Americans don't really do that anymore. They've abandoned that side. They thought that was boring a long time ago until they realized they needed that to explore on Mars, and to potentially make it a habitable planet. Okay. So hematite has wide uses. I don't know what you all know about geological time, but it's always a difficult conundrum to deal with. So we're right up here at the present day, up on the top left-hand side of the screen. And this is the standard international chronographic chart. Globally, everyone's out there looking to make sure that this is correct. And some people have spent all their lives looking and deciding whether the Ordovician boundary between that and the lower Cambrian should be at 485.4 million years ago, plus or minus 1.9 million years. And you might think, what's the point in that? Well, sometimes I raise that question as well myself, but ultimately it allows us to understand geological processes through Earth's time. And I've mentioned about the Pre-Cambrian and the banded iron formations you find in New Zealand, and this is this, in Australia, but this is this pink material here. What this doesn't really exhibit is how much time is devoted to Pre-Cambrian. 80% of geological time, not very much happened. So this is starting from the creation of the Earth as a solid planet. So not from when it became, not from when it was a star, but this is actually moving through. It's condensed, it's a mass now, and 80% of the time, all the way up to the start of the Cambrian, not very much happened. And we have at the start of the Cambrian explosion, when life on Earth suddenly started to evolve, and we come right the way through to the present day with the evolution. Cretaceous Jurassic and Cretaceous, times of the dinosaurs. So these can all be denoted out into the various times. What we're going to concentrate on this morning for the Cumbrian rocks around and for Dumfries and Galloway at that western end of the Hadrian's Wall is the Permian and the Triassic. And we're going to work our way through the Permian, looking at various rocks around Penrith, into the Triassic, and looking at the St Bees over on the Cumbrian coastline, and up around places like Annan and Cove and Kirk, Linton, which are near Brampton at the end of the Hadrian's Wall. So this is where we're going in this middle time. Just for reference, these what we also call the new red sandstones, conveniently coloured orange and purple, and ironically the Penrith sandstone is orangey brick red colour, and the St Bees sandstone is more of a purplier red, so very fortuitous. I don't think it was based upon that though. And the Devonian is the old red sandstone. So there are periods when we had these sandstones developed, and I think Ian might have a couple of weeks ago been talking about this and how you had mountain belts evolved and gave rise to these sandstones. So these old red sandstones have been derived from the closure of a massive ocean called Iapetus that gave rise to the Caledonides, which then, those being eroded, gave rise to the Devonian old red sandstones. During the Carboniferous, we had the Beriscanides, which go across northern Europe and around southern England and across through the Welsh coalfields of South Wales. When they were uplifted, they eroded and gave rise to the new red sandstone. So they're linked to major orogenic belts or big mountain belts. Right, let's have a closer look then at these Permian and Triassic age rocks. Everything from 300 million years ago right up to 200 million years. So we're looking at 100 million years of geological history. I will say quite snappily, it's a long period of time, and a lot happened during this period. And so that's what we're going to try and look into this morning. So, some of you might have seen a geological map of northern England. This is a very simplified one. A lot more complicated than this if you go to the British Geological Survey. But just let's put a few key points on here for you. You can hopefully all see the Windsill, which is where Hadrian's Wall was built on in portions. So that's hopefully familiar to you all. Then you've also got Carlisle on here. We've got the Lake District block. We've got the Vale of Eden in here, which is important. And we go off into Northumberland and the Northumberland Basin. When you start to look at the age of these rocks, Northumberland is dominated by the Carboniferous. Carboniferous deltaic sands, which makes up a lot of the Hadrian's Wall, of course. The Durham block itself, or the North Pennines, is again made up of Durham coal measures and Durham light and the cyclothems of the Carboniferous as well. And then if we come across into Cumbria, you can see there's certainly some sort of lineament or faulted structure running through here, which is quite a sharp boundary. And that's the North Pennine Fault, which actually then denotes the younger age rocks of Permian, being the orange on here, and the pinky red being the Triassic. These sweep round, they sweep round into the Solway Firth, they go offshore for most of the offshore sediments, subsea of course, but they also form the coastal portion from Whitehaven all the way down to just before you get to Barrow-in-Furness, and Sellafield is somewhere down there as well, isn't it? Well, Sellafield's just in there. And so we're going to be having a look at these a little bit later on. We note that a lot of the topography in the region, so why is Alston so high and the North Pennine so high? Well, it's because it's underlain by a granite. That granite is known as the Weardale granite. It's not exposed anywhere, but back in the 1960s it was drilled, and they found there's granite underlying it. That granite has been aged at 410 million years, plus or minus 5 million years. What's 5 million years amongst friends, I wonder? And that's the same age as the Shap granite over in the Shap Fells in Cumbria, and also the same age as the Cheviot granites up there in northern Northumberland or Scottish borders. Wind sill is 295. We can take that pretty accurately. So that records basically base Permian is when the wind sill came in. The other important feature of what we're going to be looking at this morning, geologically speaking, and not necessarily from the geological map, but is the creation of a supercontinent known as Pangaea. We also see the start, well, the change from the Permian to the Triassic. We had a massive mass extinction event, and we know that about 83% of all genera became extinct at that point. It's lucky anything survived through that. It was the largest mass extinction that we know of. It makes the mass extinction of the dinosaurs look quite insignificant in comparison. Many species died out at that time that we don't see manage to get through. So we see Permian sandstones, we see Triassic sandstones. If you look at Permian sandstones, they contain many parts of the world, lots of fossils. You look at early Triassic sandstones, they have absolutely nothing in them. They are completely barren. And so there was a big period, a massive impact on Earth. And that's partly because of Pangaea, this supercontinent developed. And I'll come back to that in a couple of minutes, why that's important. We also have a series of complex geological structures through this region, but also geologically speaking, through much of the creation of this supercontinent Pangaea, it created a very complex environment. Just to put that into context with some of the structure of the region. So here you can see, here's all these pre-Carboniferous rocks of the Lake District. So things like you might have heard of the Borrowdale volcanics, which make up Skiddaw and various other peaks around there. But we have a number of faults which kind of like compartmentalize up the region. As you can see, the Durham coalfields and the Alston block is denoted in the north by the 90 Fathom Fault, which comes out at Cullercoats on the coast, and also the Stiblich Fault, which comes across. We've also got other faults who have the same trend going up through Northumberland. And then we've got then various features which are orientated at different orientations, such as the Pennine Fault System, which comes down into the Dent Fault System down towards near Kendal and Sebra. And then we have then other systems which are further offshore, which I'll relate to a little bit later on. Essentially, everything is kind of fault bound, and the Permo-Triassic kind of fitted in around those carboniferous masses which are being generated. So that some of these faults were long-lived basement features which have been reactivated for a long period of geological time, but certainly are important for where the Durham and Northumberland coalfields were. And probably this faulting is why the coalfields actually came to the demise, because it's actually is quite complicated and means the coal gets cut up quite readily and it's difficult to predict where it was. I think that's all I want to say about that. This is just a nice image. I just took this from the BGS website, but it just shows really nicely on how, where we have underlying granites, which are Devonian age, we have upstanding blocks. So the North Pennine Weardale granite gives rise to the Alston block. If we go further south, we have the Wensleydale granite, which gives rise to the Asquith block. So these are underlying blocks which during the Carboniferous were upstanding, and they actually are a source for some of this sediment. So some of the sediment that we see in these red sandstones directly came from these upstanding blocks that we see, because the Triassic sands and the Permian sands are all filtering in around the edge of these upstanding blocks. So we have like a bit of a sinuous pathway which the sands were probably actually moving around. So we've just looked a little bit at the stratigraphy of the Permian and Triassic. So we know it's everything from roughly 300 million years ago right up to 200 million years ago. But we can go a little bit further than that, and that's what we need to do this morning. And essentially, we're looking at a number of different units. And this figure here at the bottom, which shows them here, is quite nice. There's other contemporaneous deposits found elsewhere in the Dumfries and Galloway area, but I just want to just concentrate on the Vale of Eden and the margins of the Carlisle Basin, whereby we have a number of different formation names, and particularly the Penrith Sandstone and the St Bees Sandstone, which are both red sandstones, but formed in very different environments. Casually looking at them, they look very similar, but when you start to look in detail, you can see a lot of differences. But what we do note is wherever we are during the Permian and Triassic, we have a dominance of what we call aeolian or windblown sands, big sand dunes. We have evaporites, which similar to what's being precipitated today in the Dead Sea of Israel and Jordan. And we have lots of ephemeral, and I mean ephemeral temporary to possibly perennial rivers. So they sometimes had water in them, sometimes didn't. And this denotes a change as we move up. So we're going from a period of probably hyper-aridity during the Permian, when everything was very arid, not much rainfall. There must have been some water in the system, because sand dunes don't form unless there's slight dampness on the dunes, because if you've ever tried to build dry sandcastles on the beach, they don't stand up, do they? So you need a little bit of water in them to create the sand dunes. And as we move through the Permian, things got slightly wetter. And as we shifted into the Triassic, things became a little bit wetter, but then go back drier again towards the end of the Triassic. So we have this climate change, which seems to have some sort of influence upon the sediments. Before we go and look at the actual rocks themselves, we need to put this into some context. Why is this actually taking place? And I've already mentioned about this supercontinent Pangaea. And I think it's important for us just to be able to appreciate that, what was actually happening. Now, I've taken these from Scotese's website. You've got the link there. Please go and have a look at that. There's lots of 3D globes, and you can see as a movie of plate tectonics through geological time, which is absolutely critical for our understanding. And Scotese and lots of other people have spent their working life just trying to work out the plate tectonics, what's actually going on. A lot of information has to be inputted into these models just to be able to generate them. On paleogeographic globes, as we can see here. So starting from the late Carboniferous in the top left, so just prior to the start of the Permian, you can see things were starting to come together, and we have something early continent called Pangaea. Again, this is Americanism. There's an A usually in the English spelling we pop in. You see that various Gondwana was starting to change. There was probably ice caps on the southern part of the globe. And then as we start to shift into the Permian, that became a lot more robust. The continents all came together and create the classic Pangaea supercontinent. This is when all the world's continents came together as one critical mass. There was nothing else roaming around, everything was together. So it's not like today where the African continent is different from the South American continent because there's an ocean called the Atlantic in between. You can see that with present day plate tectonic settings kind of superimposed on this, you can see that there's the outline of South America, here's Africa. They were together as one. If you walked across it, you would not have known there would have been any ocean there at all in a few 100 million years. This is absolutely critical because this gave rise to a very strange environment. Because if you are in the middle of that environment, your climate is going to be pretty harsh. You're going to have very, very hot summers, possibly quite cold winters. We see that in Siberia today, where it's a very harsh environment to live within, with quite extremes in climate. That started to break up. And more or less, as soon as Pangaea was created, it started to disband. Because plate tectonics is an ever-going dynamic process. And as soon as things came together, things started to rift and wanted to push apart. And as we move into the Triassic, Pangaea started to break up and we get lots of narrow seaways, lots of what we call rifts. And that's exactly the case for the UK. And you can see here, the UK is indicated there as a modern day geometry of it, right within a rift system. We are starting to form the new Tethys Ocean. The remnants of Tethys is the present day Mediterranean Sea, but actually started to incur. And during the Triassic, we get progressively more humid, perhaps slightly more monsoonal climate compared to the really hyper aridity that we see during the Permian. And as we shift into the early Jurassic, I'm not going to talk much about this, but it just shows that from essentially the end Triassic, early Jurassic times, we start to create modern day plate tectonic framework. So the rifting between South America and Africa starts to initiate and really starts to get going later on during the Jurassic into the Cretaceous times to give the present day plates configuration we see. So everything came together in the Permian and virtually started to break away again during the Triassic. That grouping together gave rise to this harsh climate and can be accounted for to some extent by the rocks we actually see. So let's look in a little bit more detail at the UK then, shall we? This is from some research I did some years ago looking at the Orc field. I sold my soul to the devil a long time ago, and I used to work for the oil industry, and I actually worked a lot in the southern North Sea gas basin. The Orc field is a Permian age rock, same as the Penrith Sandstone. It actually is a producing gas field, has been for many years, and it's probably what's kept the lights and the heating on in our houses probably for the last 20 years. What's important about this is looking at the map. Here's the outline of the UK. And you can see over here on the west coast, where we're particularly interested, you can see all these yellow sands, which are the Aeolian dune sands of the Penrith Sandstone. Really quite important because it forms a much bigger belt. So the southern North Sea gas fields are all part of the same age. If anyone's ever been around Durham and know south of Durham, a place called Bowburn at the A1 interchange, there's a number of quarries around there which take out the magnesium limestone, but just underneath that is the Permian yellow sands. They're yellow in colour because they don't have much hematite in them, so they haven't had that orange coloration, but they're exactly the same age as the sands we see in Penrith, the lower Permian sands over there. So we have this large dune fields of the early Permian across much of northwest Europe. These dune fields go right the way down into the Netherlands and across all the way over to Poland as well. So big belt of Aeolian dunes. By late Permian times, we see there's start to be subtle changes. I mentioned before about Tethys, this new sea starting to come in, and it's starting to flood various portions. So when the sea rose, it flooded various areas of the southern North Sea and across into Poland and Europe. But you can see here, there's a start of initiation of some sort of a connection from South Devon up through past Bristol, up through the English Midlands, up through the Cheshire Basin, into the East Irish Sea, and maybe even swing round, back round into the Vale of Eden. And so we have this large system here of sands which are recorded, and also some evaporites as well, these gypsum and anhydrites, which are classic out here in the North Sea. But over here in the Vale of Eden and Cumbria, Kirby Thor is a good example of where they mine some of that salt. Not as thick as in the North Sea or southern North Sea, but certainly important. As we move through into the Indian is the first stage of the Triassic, so don't worry about that, it's this early Triassic. You can start to see that this system perhaps is still there to some extent, some sort of system flowing up here. We have a bit of a change in the North Sea, which is kind of connected in a bit of a contortuous route around. So there's certainly, where we see the Cumbrian geology, it's not just isolated, it's actually linked to a much bigger picture. It's sometimes difficult to comprehend that though. And lots of these maps have been created over the years because of us understanding the exploration of these regions. Then as we move through the Triassic, you can see that the early Triassic, slightly later than the previous slide, you can see this dominance of this river system coming up from the English Channel, probably originated from somewhere in the Brittany region, all the way up through the English Midlands, up into the Cheshire Basin, giving rise to all the East Irish Sea gas reservoirs, which are Triassic red sandstones, the same as we see of St. Bees age. And then as we move through into later Triassic times, we have a slight change in the system. We go into what we would call Mercian mudstones, more mud dominated, slightly odd environment, probably shallow lakes, maybe with a little bit of evaporation and halites forming within it. In the North Sea and southern North Sea, a linked system, we go into something which we call the Skagerrak Formation, which is a massive fluvial system flowing down from the north, probably from Greenland into the North Sea, and petering out. It doesn't go any further than the North Sea, it stops, but was probably a river system of certainly over 1,000 kilometres, if not longer. And branches of that comes down around Scotland, in between Northern Ireland and the Scottish borders, and down towards the Isle of Man, and kind of they peter out there and interfinger with material coming up from the north if there was still available. A lot of it becomes more lacustrine, the shallow lakes with lots of evaporation taking place. So what happened then? Well, this supercontinent Pangaea, associated with all sorts of other factors when we have all the continents coming together, gave rise to this very harsh environment. And this harsh environment gave initially a very arid climate. And as we start to move, and the plate started to move from the Permian into the Triassic, we shifted slowly northwards. And we start to get a wetter, perhaps slightly more monsoonal climate, especially as the Tethys was starting to encroach onto our area. So prior to that, the sea was well away. There was no incursion of the marine realm into this area, and everything was hyper arid. And so you've got sand dunes and you've got evaporites, high evaporation of any groundwaters that were taking place. As we shift into the Triassic, things get progressively a little bit wetter, and we can see that recorded in the rocks because we're getting more fluvial input coming in. You can start to link this across much of Europe. So this goes into the Western Tethys, and also into the Norwegian Basin, and up northwards in the Barents Sea is north of Norway. So you can see there's a very similar changes that occur across the region. There was also some volcanism occurring at the same time, which might have actually caused some reasons for why the actual mass extinction event at the end of the Permian could have been quite so dramatic, because the Siberian traps happened right on the Permian-Triassic boundary. Lots of CO2 probably was given off, quite catastrophic, along with the combined effects of bringing everything together. Once you bring the plates all together, you reduce the amount of surface area you've got in shallow marine settings. And if you reduce down the amount of shallow marine settings where most of the creatures were living, you kill them off. And so there were organisms that managed to survive, but others got subsumed because there just wasn't an environment left for them to live. And the harshness of that environment was the most extreme indeed. So that's partly the reason why the PT mass extinction is so important for us, geologically speaking. Okay, so let's set the scene a little bit. So we can see this desert environment progressively getting wetter as we move into the Triassic. So can we see that in the rocks then of Cumbria? Well, the answer is yes, we can. And that's what I'm going to do in this second part of the talk, is work our way through actually how the rocks allow us to interpret that environment that we've just looked at. So let's start at the bottom then, shall we, and work our way up. It's the easiest way. It's the stratigraphic way that we would work. And this is the brockrum, the lower Permian brockrum, widely used in the centre of Kirby Stephen. I noticed this some years ago. I was going on holiday to the Lake District and just stopped there, and I must have some very funny looks as I go around taking pictures of the building stones, just because I've never seen brockrum used previously as a building stone. And the Kirby Stephen seems to have an awful lot of it in the centre. It's an unusual rock in that it is made up predominantly of a grey limestone clast. These are grey limestone clasts. You can see it's got a grey hue to it, even though it has some reddened coloration. The limestone clast is Carboniferous in age, it's Carboniferous limestones, and this is at Hoff Burrell's quarry, which is just south of Appleby. So if you go through the centre of Appleby, you'll get to Hoff Burrell's. And this quarry is in a farmer's field. Now, what you can't see, the other side of these trees on the left-hand side of the screen here is the exposure of the Carboniferous limestone. And basically, it didn't have very far to travel, the limestone didn't, hence that's why they look quite large, quite angular blocks of material within it. But there's also strongly reddened material, which we know would come from hematite, but most of that is quite granular, quite quartzose in its origin. So how did this occur? We can see stratigraphically it's quite restricted, seems to occur at the same time as perhaps Penrith sandstone. And the generally accepted interpretation for the brockrum is it probably was some sort of alluvial fan. So these are material coming off from uplifted blocks, shedding material straight into some sort of depositional basin. We can see it in modern day mountain belts. We can see it all over the world that fans still occur where there's something that's been uplifted, whatever that is. It will slowly be eroded, and that detrital material is just immediately deposited, because it might flow a little bit, but because of the horizontal expansion, if there's no confinement of it, it deposits its load very quickly and gives rise to what we call these alluvial fans. They're fan-shaped in geometry. They're very coarse-grained, and the coarser they are and the more angular they are would indicate that the material is transported even less distance. We know that's the case if you think about it, because going back to what I showed you some of those images before, the structure shows that we have these large upstanding blocks of Carboniferous stratigraphy lying around everywhere, with these kind of contorted roots in between, which the Permian and Triassic was actually infilling. And strange enough, the upstanding blocks were made of Carboniferous limestones, and they were incorporated into the brockrum and gave rise to some of the first deposited Permian sediments. Alluvial fans are particularly common in desert environments where you get suddenly a flash flood, high rainfall just suddenly happens, and it just sweeps out all the loose, unconsolidated material out of these upland channels and just splays out onto a basin floor. You see them in many parts of the world today, and they're quite common in the rock record as well. So the Brockram records a very coarse end member of the sandstone spectrum, which would indicate very locally sourced, incredibly locally sourced, probably to the extent where, as we can see with the Brockram, we can walk 10, 20 meters and we can see exactly where that material has come from, which is fantastic. But as we start to erode material and transport it over a greater distance, the sorting improves. And so we can go through things which are perhaps moderately sorted to incredibly well sorted. And things which are incredibly well sorted tend to be what we call more mature in their nature. They will also have much better rounding. The grains within them, or the clasps within them, will be very well rounded indeed. And so beach deposits, because they've probably undergone several phases of reworking, are much better sorted than an alluvial fan will be, because an alluvial fan has to be very close to source. Equally, aeolian dunes or desert dunes fit in with being a beach deposit because they're incredibly well sorted. If you've ever been in a desert, I don't know if anyone has, and been in when there's been suddenly a storm whip up, it's like having your face exfoliated because you have these little tiny sand grains which actually just hit your face, and it really hurts. It really does. So you have to cover down, to hunker down, and just hopefully that sandstorm has blown through. They are incredibly abrasive. So if you imagine that hurts your face, and these sand grains are touching each other all the time, moving around, they're going to break the angular corners off and round very quickly. So anything which is aeolian or windblown tends to be quite mature down this end, and also gets rid of all the other muck in the sandstone. So if you look in Monday River Weir or the River Tees, it doesn't look the cleanest of rivers. It might well be. It has salmon in it now, don't they? But they are not that clean because they don't look clean because they contain a lot of suspended mud and sediment. That will then be incorporated into the sandstone, and that's why river sandstones tend to be this intermediate member, whereby there could be some rounding in them, but there's going to be lots of other mud and other debris within it. So as we start to increase the maturity, we remove that debris. And so this diagram here from Pettyjohn in 1987, which is widely used, allows us to start to classify sandstones based upon their content within them. And their content kind of reflects to us how mature a sandstone may be and gives us an indicator of what environment that might have been deposited within. So something which has lots of rock fragments in it, as we've seen with the Brockram, will be likely to be very immature, very local to source. Something that has lots of quartz in it, so at least 95% quartz with very little else, is going to be very mature and is more likely to be reflective of a beach sand or perhaps a dune environment. Somewhere in the middle ground here, whether something's got feldspar, rock fragments, whatever in it, doesn't matter, is more likely to fit with a river, or perhaps some of the Carboniferous sandstones of deltaic environments, whereby they tend to have a lot of other material mixed in. You can have rock sandstones. We don't see them locally around Cumbria, but you can have sandstones which have at least 10% matrix, so mud filling in between the grains of quartz, and we call those a grey wacky. They're grey in colour, typical of being deposited in deep marine settings where mud intermingles with them. So why have I gone on about this? Well, it's important to appreciate because the Penrith sandstone that we're going to look at in a minute fits right up here. The St. Bees sandstone that we're going to look at a bit later on fits over here. So just by looking at them petrographically, we can tell there's a difference in the environment, and that's partly the evidence we utilize for understanding about sandstones and their origin, and maybe piecing together what actually happened, several hundreds of millions of years ago. So Penrith sandstone then. One of the classic sandstones in Cumbria, makes up much of Penrith, which is named after, but also forms most of the sand on the south side of, or south western side of the River Eden, through much of that region. This is where it gets a bit confusing, because on this map here, it shows you that you've got the pink is the Appleby group, which is the Penrith Sandstone, and on the other side, you've got the St Bees Sandstone. And at places like Dufton, right up on the North Pennines, you can actually have close proximity of within walking distance St Bees Sandstone and Penrith Sandstone. And I know in the village of Dufton itself, there's buildings made of Penrith Sandstone and buildings made of St Bees Sandstone. And most people just always think Vale of Eden, Penrith Sandstone. That is not the case. Both sandstones exist there. And there's about 50 million years between that sandstone and that sandstone. So it's quite significant. So what makes the Penrith Sandstone so special then? Well, it's bright red in colour. It's highly granular, it's medium grained, and it's found pretty prominently along the River Eden. Anyone who's been along the 66 has probably caught glimpses of red sandstone around there, or if you've been walking around there. And this example here, which I'll show again in a few minutes, is from Lacey's Caves up near Lazenby, and has this fractures running through it. So I don't know if anyone's been to Lazenby's Caves. They're a bit of a folly, I understand, that were built back in Victorian times, or carved out of the rocks, maybe enhanced from previous development, I don't know. But they have all these fractures running through it, which are quite important. So, what do they look like? Well, this is looking at the sandstones under a microscope, under a standard petrographic microscope. I don't know if anyone's looked at sands under a microscope previously, but essentially we will put the sample of rock, we'll make it into a thin section, and we'll put them on a glass slide. They're always cut to 30 microns, which is a standard thickness, so we have the standard optical properties of the minerals. That's for all thin sections for whatever rock type. We want to be able to make sure that we're looking at the standard practice here. So these three, the top two and the bottom right, are in standard light. This is the bottom left is when we go into cross polars. So if you get two Polaroid lenses out of your sunglasses and you put them at 90 degrees to each other, you block out all light. I don't know if you've ever done that, but if you ever have one of your lenses drop out your sunglasses one day, hold them up to the light and hold them to 90 degrees to each other, and you can't see anything through them. But if you play around with those combinations of how you alter that, you can actually polarize the light, and you can have different optical properties. And so this is under polarized light, which is specialist for material scientists and for us geologists. Our microscopes have this added function added to them. But the Penrith Sandstone itself, if you look at it, you can see it's got, these are grains, oops, what's happened there? Sorry. These are grains of quartz within it, quite well-formed quartz. You can see them all the way around, doesn't matter whatever form it is. There is some other grains in here. So this grain here, I'm pointing to now with the stripiness to it, is a piece of feldspar, slightly eroded. Feldspar does erode in these rocks quite badly. And this grain here is a bit of lithic, or a bit of other rock. I say other rock, don't quite know what that one is. I'd have to do a bit more work into that, but it's just a fragment of rock from somewhere else. But what's critical here is you can see the hematite. And the hematite is this reddy brown dusting on top of the quartz grain. But you can see it's kind of embedded within the quartz, because there's the quartz grain here, you've got this hematite coating, and then a bit of quartz on the outside. What actually happened is that the quartz was initially deposited with a hematite coating on it, which developed over some time, probably during shallow burial. And then during deeper burial, and I'm talking here probably 1 to 2 kilometers of burial depth, where it was more deeply buried, you then have quartz coming out of solution and precipitating onto the surface, giving rise to an extra coating. This is where it's quite critical, because the hematite preserves the original shape of the grains. And the original shape of the grains is highly rounded. If you use the present shape of the grain, which is highly angular, it will give you a bit of a misinterpretation of what was actually going on. So let's have a look at that then. So this is a little bit more of a closer up view at this, but you can see this hematite coming around the outside edge. There's the quartz grain itself, and then you can see here there's more hematite, and I've called this a quartz overgrowth. These quartz overgrowths are important because when they grow onto the surface of the grain, they grow in exactly the same crystallographic orientation for quartz. And so when you rotate them on a microscope, they actually follow exactly the same crystallographic form of the primary quartz crystal. That becomes important when you're looking at these rocks to understanding when these different events occurred. And for me, for looking for oil and gas, that's particularly important because these later stage events start to fill the pore space. And the pore space on here is stained blue. So to make these rocks, we have to inject an epoxy resin, which we stain blue into the rock. The epoxy resin fills all the pore space, which makes our job that little bit easier in understanding what's going on. And we don't really want much quartz overgrowth because that starts to fill the pore space. Less pore space means there's less potential for storage of water for an aquifer, storage of oil and gas for an oil reservoir, or storage of CO2 if we want to look at it for CO2 subsurface storage, which is probably the big buzzword at the moment. You can also put in here, you can see that if you look at some of these grains in great detail, you can see there's the quartz overgrowth, and there's a nice little bit of the reddy brown hematite. And some of these, when you look at them, you can see individual plates of hematite growing, which is really quite lovely actually within this sandstone itself. But what about, I just showed before, so we can see there's definitely a hematite in here. It's grown and developed, and they're very well-rounded grains, which would depict some sort of Aeolian setting, perhaps. But we can see these large numbers of the outcrops we go to, and you can see this lovely red sandstone has these fractures running through it, which is quite characteristic of many of the outcrops in the Vale of Eden. And that's primarily because if you go back and look at the maps, I'll just whiz back to it now. You can see that the Vale of Eden is located very close to this black line here. And this black line is the Pennine Fault, which was active, or we certainly think was active post Penrith deposition, post the accumulation of these sands. So what does that entail then? Well, the movement of the fault probably gave rise to fracturing. So the sands were deposited, probably semi-coherent, and they actually were starting to then be moved and jostled around and started to create fractures, what we call deformation bands. These deformation bands then are prone for fluids to pass through it. The Pennine Fault probably brought fluids up, but there have been fluids passing through the rock anyway, and those are enhanced pathways for fluids to pass, and fluids will readily precipitate in them. Many of these deformation band features and form cross-cutting patterns across the sandstone are filled with quartz as well. So it's locally sourced material. So if you ever get the chance to go to near Lazenby, to Lacey's Caves, I can thoroughly recommend it because you can actually walk within them, and it's amazing on the fracture network and the pattern that is created in the rocks. So certainly a worthwhile place to go and have a look at. But these are caused because of the fracturing related to the Pennine Fault post their deposition. So it's nothing to do with the depositional setting. It's a post process which has been implemented into the sandstones. That in its own right, I thought I'd show you some high-end stuff that we can do. So we don't just use a standard microscope. This is from a £750,000 microscope called a ChemScan. A ChemScan is a quantitative mineralogy microscope, which allows us to put a sample onto the microscope stage, and within about 20 minutes, we can have a full elemental distribution map of what is in that rock. It's quite amazing on how it achieves it. The longer we leave it, the more detailed it becomes. And just simply here, from work I've done previously, shows that if when we look, just go back one here a minute, you can see there's a coloration difference in some of these deformation bands. Some of the deformation bands seem to be whiter in color, whereas the sandstones themselves are very strongly reddened, which doesn't always make sense. They should be, they're utilizing the same material. So something else happened to the rock for this discoloration to take place. And when we look at that, we can see the bleached and the unbleached. So this is the classic Penrith sandstone. This would be the infill of some of those bleached units. And we can see that it looked discrete on here, but you can see that the main difference is they contain, the bleached units contain a little bit more of the mineral, clay mineral called illite. And we'll look at illite when we go to the St. Bees sandstone, and another mineral called kaolinite. And the kaolinite, we think, actually comes directly from the breakdown of the feldspar. Some of you might have heard of kaolinite. It's the white clay mineral found in St Austell in Cornwall from the breakdown of the granites there, and it's used as an agent in cosmetics, as a bolstering to bolster out the cosmetic. It's also utilized for whitening paper. It's a very white mineral when found. Here, it's not red here. This is an artificial color we add to make it easier to see these minerals when we're looking at it. Just bear in mind, this is 1 millimeter, that is, so we're looking at a 4 millimeter by 4 millimeter view of the rock. So very, very detailed indeed, but this is the detail that sometimes we have to look at when we're looking at the understanding what happened to that rock over a period of time. That's the Penrith, so bright red sandstone, well-rounded grains, probably formed in a desert Aeolian dune environment. What about the St Bees then? So that's found on the other side. You can find this in Dufton, and classically this is from St Bees railway station, which is built of the St Bees sandstone. Fortuitously, it'd be rather ironic if it was built of Penrith sandstone, wouldn't it? But these are much younger. So we've missed out the Eden shales now. So these are found around Kirby Stephen and Kirby Thor as well. They're just white rocks. We only ever see them in the subsurface. Problem is with the Eden shales is when they are exposed at the surface, they erode very quickly indeed, because evaporites are not stable in our climatic conditions that we have in the UK. So there isn't really much to see with them. So let's go up now into the Triassic. So now we're coming out of that Pangaea supercontinent where everything was together, hyper-aridity, and we're moving into the Triassic where things of Pangaea are starting to move apart now. And we can start to see the sandstone looks subtly different. It's red, yeah, but you can see that it's not bright red anymore. It's got bits in it. It looks a bit more dirty. It's slightly more feldspar rich. It has a little bit more components within it, not so quartz rich. So let's go and have a look at the classic exposures of the St Bees sandstone before we come back, and we're going to look at them a little bit closer around the western end of Hadrian's Wall. So this is where I don't know which came first, the sandstone or St Bees head. I suppose it's a chicken and egg, what came first, isn't it? In that the St Bees sandstone are classically formed around St Bees headland, so Whitehaven, just up there in the north. Popular today on the news, I saw, because of the issues about the coking coal mine going in, taking out the Carboniferous coal just offshore here. I know that the government have given the go-ahead for that, even though they've got CO2 targets they want to meet. But actually fits in nicely with our story, because they're actually building their plant on the St Bees sandstone. They're choosing to build it on the St Bees sandstone because it's a nice stable substrate to build upon. And then we've got this headland here. If you ever want to go for a nice circular walk, get the train from Whitehaven, leave your car in Whitehaven, get the train to St Bees, jump off the train in St Bees and walk down, and you can do a lovely coastal path about 6 miles back to your car back in Whitehaven. It's a really nice walk to go and do. And you will get to see some of this spectacular coastline. Here's the coastal path up here. And this is at Fledswick Bay. It's just here, about halfway along the walk, and you can see this spectacular, shallowly dipping red sandstones, sand on sand on sand on sand, all the way up through it. The sands themselves have erosional bases. They taper out laterally, and they're recording a series of sheet sands being deposited in an ancient river setting. Some of these sheets were temporary, others were a little bit more long-lived with water within them. Probably the water depth was probably only no more than maybe 0.5 meter, a maximum. Very little lived around that time, but certainly there was a lot of water around, and lots of this fluvial stacked channels were being evolved at that time. We know there's rapid sedimentation, so these sands were coming in on top of each other very quickly indeed. Because we can see that in the sedimentary structures. This is a sand volcano. So this is where fluid in the sand is becoming pressurized. Essentially, you can't compress a fluid. So if you start to lay wet sand on top of wet sand on top of wet sand, eventually those wet sands at the bottom, the fluid is going to be so highly pressured, it will want to find a fracture or something to work its way out. And that's how we create these sand volcanoes. There's also some muds as well, so not all of it is big thick sands. There's muds intercalated within it as well, so quite a lot present there. This quarry here, Burkham's quarry, is used by Marshalls, the aggregate company, and they take out large blocks of sand here. It's highly prized. The sand is here from this location for buildings all around the country today, and for flagstones and for fascias. They make lots of fascias of buildings, and that sort of cladding system that they utilize from this St. B sandstone. So that shows the classic, the very different style here, and it looks very different to the Penrith sandstone. It's got a more of a purpley colour to it. It looks mucky, and you look at it, and it is a mucky sandstone. You can see it's sand, but it's got a lot more clay within the system. Let's go further north now, and this is a place called Cove Quarry. Cove Quarry is north of Gretna Green. So if you go up the M6, come off just north of Gretna and head towards Annan, you'll go past a place called Cove Quarry. Again, it's a quarry which is utilised. They only use it for 6 months of the year, and again they take out the St. B sandstone here. They pump out all this water in the bottom of the quarry, and they get an extra 15 meters of water depth in here and exposure to take out. And the best sand is unfortunately underneath this water depth. And the only time they ever let you go in the quarry is when they're not operating. So I can never get to see it when it's not there. But there's some fantastic structures. Again, you can see stacked sand on sand on sand. But within this quarry, you can see some of the more subtle structures that evolved in this ancient river system. You've got little ripples, look as fresh as what you might see on the beach today, but these were forming in a river system. You've got what we call flute marks. So these are erosional scours in the base of the river, which was scouring along on a muddy substrate. And this is upside down, so they would normally be on the underside of the bed that you look up to. You can see some lovely dune structures in the base of the river. So this is a preserved paleo surface. So the hammerhead is actually lying on the dune. So this would be an inclined form in the river base where water would have flown up and over that dune. And you can see that recorded in some of the cross beds above, whereby it gives rise to the movement of the water being preserved in the sand. Then here, we know that it wasn't wet all the time. There must have been periods of drying out. And these are what we call desiccation cracks. You can see this polygonal shape here is where you see the mud is contracting because it's dehydrating and causes these cracks within the sediment. And these then get preserved by the next infilling, usually with sand, into the cracks. And you hence get this, what we call desiccation cracks or dewatering features. So quite a lot happening there, quite a lot of structures you can pull out and understand. But again, you can see it has this purpley colour rather than the real strong brick red colour that you see for the Penrith. The sands themselves are highly elaborate with what they contain because they have more muck and rubbish in them. They have a lot more going on in them. And you look in the standard microscope in the top left corner, you can see it looks mucky. It's dirty. It's got lots of more angular grains in it. It's got these yellow crystals, or what we stain yellow, are feldspar. The blue here is porosity, so it does have some porosity in it, but it has a lot more material. It has a lot more kaolinite. These are some classic pictures, not actually from the St. B sandstone. It's a bit too difficult to see, but you can see they form these books of clay, very classic. Looks a bit like a concertina, or what we call a book. And then you also have lots of illite. Illite is another clay mineral. When it starts to form, it can actually degrade your porosity and permeability in the rock very quickly indeed because of the fibers it develops. There's another mineral here called chlorite. These tend to grow as coatings on the surface. And you can see here where they grow on the surface of the grains, it stops any further quartz cementation. So quite important during burial processes to have grains coated in chlorite, but not too much. It's a fine balance. So we have lots of different minerals in here just within a sandstone. So on the surface, you just think, oh, okay, it's red sandstone, lots of quartz in that and probably some hematite. But when you look into more detail, you can see it contains an awful lot more, which tells you something about its history, how it's been buried and to what depth to allow some of these minerals to directly precipitate. And finally, from this section, is the Kirk Linton sandstones. These are near Kirk Linton, just to the north west of Brampton. If you ever go over on the A69, you go along the road towards Longframlington. I can't think of the name of the place now, but you go over the River Lynn, which is near Kirk Linton, and you see the Kirk Linton sandstones. And the first thing you note about when you see the Kirk Linton sandstones, these are younger than the St. Bees. They overlie the St. Bees sandstone stratigraphically, but you can see you immediately go back to a change in colour. They are bright red, and they look very much like the Penrith. They're not, but they are Triassic in age, and these are again going back to an Aeolian wind-blown environment. So there's the increase in aridity. We're going from something which is a bit wet to something which is drier. They do have some wetting within them because we can see there's ripples here, and these ripples probably occur between the dunes in the interdune area, whereby it might have been wetter and maybe in the odd stream flowing down through them. And when we look along the river section, the river is at the bottom of this photograph here. We can see that there's these dunes. That's about 1.5 meters high there. And you can see this dune, and then there's the foresets with the avalanching of the dune facies or sands down the foreset. So we know the wind direction was from left to right for that dune. And they're stacked all throughout this section here. We're preserving these lovely dunes. They're not as big as in the Penrith because we think the area was probably a little bit wetter in some periods, but also probably the wind was a little bit more intense, which blew the dunes out. If you don't have, you have to have the right current, wind speed, etc., all sorts of characteristics to allow dunes to get to really large sizes, which of course they can do, but if you don't have that, they get blown out very quickly. But they still preserve the characteristic feature within the sandstone that we want to look for. So we've seen it in the Penrith. We can see it in these Kirk Linton, especially in this grain here. And you can see how rounded these grains are. So again, are depicting these have been abraded, they've been moved around, they've been abused and chucked together in these Aeolian sands. And so again, the actual petrography or the sand grains start to indicate a little bit about what's actually going on in the sands themselves. And you can see these are the sand dunes here in the Kirk Linton section. The road across this River Lynn is just to the left there. And this is just an interpretation of what some of these sand dunes perhaps look like, with various reactivation surfaces where maybe wind direction changed, or there was abandonment and then the wind brought more sand in a bit later on. Not as big as Penrith sands, but certainly important. These are important because they're the same as the Ormskirk sandstone in the East Irish Sea, so offshore Liverpool, and it's these sands which have given rise to the gas potential in that field over the last 20 or 30 years, and is still important today. And I'm going to explain why that is in my last few slides, why it's important. Before we do, let's just summarize and bring some of this together. This is from Tyrrell, Shane Tyrrell, who's at Dublin University in Ireland, and he reconstructed what he thought was going on, namely on the Irish sector, but that so happens fits with us quite nicely as well, in that you had this river system. So north is top of, so you can see here's north just for bearings. So we had the remnants of the Variscan mountain belt, that Carboniferous event that happened. We can find elements of that across South Wales as well, across southern England. But we had river systems being derived from this mountain belt, flowing up through maybe the Wessex Basin, through Devon and Dorset, up through the English Midlands, up through the Cheshire Basin, into the East Irish Sea. And on here, this would be the Vale of Eden. So it just gives you some reference. We have the other systems coming from the north. We have material going off to the west of Ireland, of which of the same age. We have the Corrib gas field, the only major gas field that the Irish actually have in production at present. And we also have, at the same time, various large dune fields happening and fluvial systems over in the southern North Sea gas basin. That puts it into context here just a little bit more. Looking back at the map we showed you earlier, with this system coming up through central England, maybe branching off, going up through to Humber, linking with the southern North Sea, and then we have these systems flowing from the south downwards into this region as well. So a big network. And as we move from the Permian into the Triassic, things progressively got a little bit wetter for a period. As we know, the Tethyan realm started to come in down here. This Tethys started to give maybe a slightly more monsoonal climate. Some work I published some years ago now looked at actually how this interrelated to the East Irish Sea gas basins, where we have really good coverage, lots of wells drilled out here and producing. So we can see there's a whole series of, in A, the fluvial system coming up from the Cheshire Basin up into the East Irish Sea, moving and swinging around into the Solway. We got good evidence that there was some sort of fluvial system coming across through here, which gave rise to the St. B sandstones that we see around the Annan area and in that northern portion of the Vale of Eden. Probably something going off down into the Vale of Eden. Whether it connected across Northumberland into the North Sea, we're not sure. What we do know is that by the time we move through into later Triassic times, into the Kirk Linton, we had an Aeolian source coming here. Aeolian dunes dominated, and the river system, which still existed in the East Irish Sea, shifted perhaps further to the west rather than over towards the east. Maybe something to do with the Pennine Fault, an uplift on that, an uplift of these blocks. We don't honestly know, to be honest. But what we do know is we had a period of, during the Triassic, period of fluvial systems, which interestingly ended. So we had this system coming all the way from Brittany, all the way up through the UK, and just stopping here. Didn't go any further. Just stopped, ended. And it's what we call a terminal fluvial system. They're quite common in the rock record. We don't see that many of them today. Places like the Niles River in central Australia is a good example. Really difficult to understand. Why do they end? What happens to them? You know, we always think of river systems flowing to the sea, but they don't have to. And this is a good example where this was actually taking place, but complicated as well. So why am I interested in all of this? not just, I'm not an archaeologist, but I'm not really have the input for Hadrian's Wall. I just thought I'd put some context to it for you all, in that as we starting to move now, most of my past probably 15, 20 years of academic research has been focused upon looking for oil and gas. I'm now having to reverse around my whole philosophy of, rather than taking stuff out of the ground, is put stuff back in it. And the Permo-Triassic potentially are excellent reservoir rocks, not just for taking gas out and oil out of them, but putting CO2 back in. And the philosophy here is that if you have a reservoir in the subsurface which is robust enough to maintain oil and gas in it for tens of millions or hundreds of millions of years, we hope it will be robust enough to do the same for CO2 to be injected within it. The problem is there's very few test sites around the world. There's been one which BP have operated in Algeria for probably the last 10 years. But that is rather odd in how it's developed, and we need to do a lot more. And hence my interest in the rocks of the Penrith and the St Bees is subjecting them to various experimental studies, which I'll show you in a minute as my final slide, trying to understand what happens when we inject CO2 into that pore space. So it's important for us to know the mineralogy. So I've given you some indications that St Bees has a lot more minerals in it than what the Penrith does. Does that make a difference? Well, it can do. It can make the rock more reactive, or it could help our situation. And so when we inject CO2 into a subsurface reservoir, we're hoping that the CO2 will actually dissolve into the pore space. Most deep-seated reservoirs, the pore space, the fluid within the pore, is made up of brine, salty water. And usually brines react quite nicely with CO2 and make them quite dense, and so they want to sink. And usually remain quite stable over time. If you have enough of it, the CO2 can react with the salt and can actually start to precipitate and then become a dense solid mass within the reservoir. There's a number of test sites being done at the moment, one in the northern North Sea, looking at the Cumbrian Sandstone, which is a fairly shallow reservoir. There's one in the southern North Sea looking at, again, a Triassic reservoir, equivalent to the Triassic we see in Cumbria, but this is actually being developed from the Net Zero project at Teesside. So they're wanting to take all the CO2 produced by the various chemical plants there and inject it into the southern North Sea, into the sandstone. And there's some talk about doing something off Liverpool Bay using Morecambe Bay gas field, which is directly into the equivalent of the Kirk Linton sandstones. The East Irish Sea is a little bit behind the other two. I think by 2023, they want to start injecting into the Triassic of the southern North Sea. Well, BP certainly do, and they've certainly invested enough money to try to move that along. What we're trying to do in Durham is try to understand what happens when you inject this into the rock. Will it become stable? And that's what we want to know. Particularly, we've highlighted that are oil reservoirs really the best sites? Should we be looking at other sites? And so we've been doing a lot of work in the Solway Firth to see whether the Solway Firth, which has all the right rock types in it, but has a much thicker shale package on top. So the impermeable membrane across the top, these shales, is much thicker in the Solway. And we're wondering whether that could be a better policy to target, not necessarily redundant oil reservoirs, but maybe new fresh terrain, which could be a better source. And so what we've been doing some experiments. So we've been taking the rocks and subjecting them to pressure and temperature. So we've been trying to mimic what might happen if we were to bury them, and then we've been flushing them with CO2. And so we have this hydrothermal reactor, which is basically like a ticking time bomb. It's a large piece of stainless steel with a cavity in the center, which we can flush with gases through it. We can heat it with a heating jacket around it. We can also subject it to pressures as well. So we can make it as realistic as we want for the subsurface, where it can be a fairly harsh environment. We then undertake these experiments using various pore fluids, And sometimes we use silica gel, sometimes we use the real rock sample. There's benefits for both, whether we use artificial rocks where we can control the parameters more, or whether we use the real rocks to try to create an end member understanding. But what we then do is the experimental rock that we take out after the experiment, we subject it to micro CT scanning. So some of you may have had a CT scan at one time or other. We're using exactly the same technology, but we're focusing the beam onto the individual pore spaces, which allows us to then reconstruct. So this is a CT scan of the rock itself that we took in the experiment. This is the same CT scan, but then we can start to look at the blue material in here, which is a new mineral precipitate, which is precipitated in the pore space because of us introducing CO2 into the reservoir. And that's really important because we want to know what happens when CO2 goes into these sands, what will actually precipitate, if anything at all, and how stable would the rock be. And then I showed you briefly quantitative SEM work. But what we can do is we can do scans of these rocks repeatedly and look for different elements and different components. So there's the basic rock with the quartz grains and bits of other pieces in it. And you can see here's an elemental map of the different elements we can plot out. And of course, by combining different elements of these, we can then catalog what the minerals are, or we can just do an elemental map. And why iron is particularly important is because I mentioned before about the mineral chlorite. If we inject CO2 into a rock with lots of chlorite, like potentially the St. B sandstone has, chlorite is prone to dissolve quite quickly. And then you release a lot of iron into the system. That iron could, over time, precipitate with carbonates to give siderite. Now, siderite is a fairly stable mineral and will start to occlude pore space. That's good, but could be bad, because if it happens early on in your injection of CO2 into a reservoir, you lose your space very quickly indeed at the injection point. And so that is a concern. The other one is actually sometimes chlorite fills cavities or fractures within the rock. And if you suddenly inject CO2 into that and you suddenly dissolve the chlorite, you create new pathways for fluid flow. And that could actually then mean the CO2 leaks from the reservoir that you think has integrity into something that may not have any integrity at all, and you can get leakage through it. So there's an awful lot of work that's going on behind the scenes at the moment at Durham and other institutions as well to help some of the old companies switch their whole philosophy. They have the knowledge, they have the money to explore for oil and gas, but they're now having to switch it back round to understand what happens when we pump stuff back in and the reactions that take place. And lots of these red sandstones from Cumbria are prime targets for CCS and CCUS for the future, and hopefully their life will come back again as well. Thank you very much, everybody. I'll stop sharing. How do I stop sharing? There we go.
Thanks.